What's up, guys? So welcome back to another lesson of system design, and today we are going to discuss about the Uber. When you tap one button, within 10 seconds a car appears on the map heading towards you. Then you see the driver's name, the car make and the model, the license plate, and the ETA. You get in, you ride, and you get out. Payment happens automatically. Now that experience is deceptively simple, but behind that single tap is a system that tracks the live location of 5 million drivers every 3 seconds. It matches millions of riders with drivers in the real time, and it calculates the dynamic pricing based upon the supply and demand, zone by zone, minute by minute. It processes millions of payments daily across 70 countries. And it does all this while preventing the same driver from being matched to two riders simultaneously. Now, today, we're going to discuss the design of Uber. We will cover the driver spatial index, the QuadTree versus the H3 versus Geohash with the real trade offs. We will walk through the matching algorithm. We will go deep on search pricing, how it actually is calculated. We will trace the full trip state machine from requested to pay. We will cover the WebSocket architecture for the real-time location tracking. We will talk about the payment processing with idempotency because payment failures without idempotency are catastrophic. And we will cover the driver supply prediction. Then we will hit the principal engineer questions. Let's go. Now let's get into it. Let's nail down what the system needs to do. The first requirement is request arrival. The rider provides a pickup and drop-off location. System returns a fair estimate. The rider confirms. Then the second is a match a driver. Find the nearest available compatible driver. We should notify them and then they should accept or decline. Third one is the real-time tracking. The both drivers and the rider see each other's live location on a map. And the fourth is the ATA calculations. How long until the driver arrives? How long the trip will take? The fifth is the dynamic pricing, the surge multiplier based on the real-time supply and demand in each zone. Sixth one is the payment processing. We do automatic charge at the end of the trip, the driver payout calculation, and then we do the receipt generation. Seventh is the trip history, where the riders and the drivers can review the past trips. Eighth is the rating system. We do the bidirectional ratings after each trip. Ninth is the driver availability. Driver can go online, offline. The system tracks their availability and the location. Then we have the multiple ride types. We have UberX, Uber XL, Uber Black, and Uber Pool. Different vehicle types, different pricing. Now, what we are not building here today is the food delivery. This is a separate system with its own constraint. The driver onboarding pipeline, the fraud detection system. Though I will mention the key signals, then we will discuss about the route navigation for the driver that uses Google Maps and which we have covered. We will talk about the driver onboarding pipeline, the fraud detection system, then the route navigation for the driver that we have already discussed in the Google Maps video. You can go back and watch the Google Maps system design where you will get a deep dive into the Google Maps. Now, the non-functional requirements tells you why this system is hard. We need an availability of 99.99% uptime. If the Uber is down, the drivers lose income. Riders are standard. Both are unacceptable. For latency, finding a matching driver, we should be done in 10 seconds. If the location updates, then it should update the driver within 1 second. For real time, the driver location should be visible to the rider with the sub-second freshness. For consistency, one driver matched to exactly one rider. No exceptions, no double booking. If you want to scale it for millions of concurrent rides globally, we should be able to do fault tolerance, survive the data center failures without losing in-progress trips. And since the application operates globally, it will be operating in 70 plus countries with different regulations, currencies, and language. We should be able to handle that. Notice the interesting tension. Location tracking can be eventually consistent if a driver's position is 2 seconds stale, but that is fine. But trip state transition must be strongly consistent. You cannot double book a driver. That tension drives many of the technology choices we will make today. Let's quickly do some of the math here. We will have 20 million daily active users, 5 million daily active drivers, 15 million daily rides. At peak, there are concurrent rides of around 1 million. Then the driver location updates every 3 seconds. About the location update throughput, for 5 million drivers, one update every 3 seconds. For 5 million divided by 3 equals 1.67 million location updates per second. Now that is the dominant write load on the system. Write request throughput, if there are 50 million writes per day, we divide it by 86,400 seconds, which equals to 175 requests per second on an average. During the peak hour, during evening rush or post-concert or stadium events, it could be 5x to 10x. Call it 1,000 requests per second at peak. For storage, we have 5 million drivers, 28,800 updates per day, and 5 bytes per update. This means 5 million times 28,800 times 50 bytes, that equals to 7.2 terabytes of location data per day. Then we have the trip data. In 15 million trips, we have 2 kilobytes per trip. 15 million times 2 kilobytes equal 30 gigabytes of trip data per day. The location data volume, that is around 7.2 terabytes per day, immediately tells you you cannot store it in a transactional SQL database. You need a write optimized time series store for the history. And you need a separate fast store, that is Redis, for the current location. After this, we will go into the high-level design. Let's walk you through the high-level design here. At the top, we have two clients, the rider app and the driver app. Both connect through a load balancer. For a real-time connection, drivers connect via WebSocket to the location service. The riders subscribe to the driver's location via the WebSocket as well. For the core service, we have the ride service, which is the orchestrator that handles the ride request, the coordinates matching, and managing the trip state. For matching service, we find the best available driver for a ride request that queries the driver's spatial index. For location service, we receive the GPS updates from the drivers, writes it to the Redis, and updates the spatial index streams to Kafka. For the pricing service, which calculates the fare estimates and the surge multipliers, it reads the supply and demand from the spatial index. The payment service charges the rider after the trip completion. It calculates the driver payout and it records in the ledger. We have the notification service, which is responsible for pushing the notification to the rider and the driver at each trip transition state. For the data store, the trip DB is used in PostgreSQL. ACID for all trip state transaction, no double booking. For the location store, we use Redis, which stores the current location per driver. It is sub-millisecond reads. Then we have driver spatial index, the real-time variable spatial index. H3 based, I will go deep into this a bit later then. The Kafka is used for sending the location event streams for analytics, traffic, and ML training. The key flow is rider, request a ride, then ride service calls the pricing service, it gets the surge multiplier and the fare estimate. Then the rider confirms, the ride service creates a trip record in the PostgreSQL. Ride service calls a matching service. The matching service queries the driver spatial index, ranks the candidate, selects the best match. Then the driver gets notified. If he accepts, then the trip state machines advances. The location service streams driver's position to rider via WebSocket. Then the trip completes and payment services called at the end. Now let's discuss about the driver spatial index deep dive. We will discuss about the QuadTree, the H3, and the Geohash. Now this is the most important data structure in the entire system. The matching algorithm depends entirely on how efficiently you can either answer the query that give me all the drivers within the 3 kilometers of the location, and you need to answer it under 50 milliseconds. That is thousands of times per second. Let's look at the 3 main options here. Option 1 is Geohash. Geohash encodes latitude and longitude on a base 32 string. It's like NQ8YY. This covers a region in San Francisco. Each additional character narrows the area. To find the nearby driver, you compute the geohash of the pickup location. Then you find all the geohash cells that are neighbor to the precision level. Now, the type of query we use here is give me all the drivers where geohash starts with 9Q8YY or its neighbor. Now, here's a problem with geohash. Cell shapes are rectangle, not uniform. Cells near the poles are much smaller than the cells near the equator. The biggest problem is the edge effects. Two points that are physically 50 meters apart can have completely different geohash prefixes if they are near a cell boundary. Now, a driver on one side of a cell boundary or a rider on the other side of the cell boundary, both within 100 meters, look far apart in the geohash space. Geohash works for simple use cases, not for a production matching system at scale. Then we have an option 2 called QuadTree. QuadTree recursively subdivides the world into 4 quadrants. You subdivide more finely in the dense area. Manhattan gets finer subdivision than the rural Wyoming. The tree adapts to the driver density. QuadTree is a good for unevenly distributed data, which driver locations definitely are. The problem is, it is an in-memory data structure. It is hard to shard across multiple servers. If one city's QuadTree grows too large or its servers fail, you have a problem. You can partition it by city, but the QuadTree for New York City at peak hour is enormous. Now, the QuadTree is the right answer for a simpler version of the system or for a smaller city. At Uber scale, H3 wins. Let's discuss about the H3 hexagonal index. Uber literally built the H3 for this problem. They open sourced it. H3 divides the Earth into hierarchy of hexagonal cells. At resolution 9, which Uber uses for matching, each cell covers about 175 meters. Now, why hexagon? Every hexagon has around 6 neighbors. Every neighbor is exactly the same distance from the center. Unlike the square grids where the diagonal neighbors are farther, this uniform distance property is critical for matching. When you want all the drivers within 3-kilometer range, you take the H3 cell for a pickup location and expand outwards using the K ring. A K ring of radius 2 gives you the center cell plus all the cells within the 2 steps. Each step is roughly 175 meters. So the K ring of 20 covers around 3.5 kilometers. The database query in this will look like: get the H3 cell for the pickup location, get all the cells in the K ring of radius 20, and this returns about 1000 cells. If you want to query the drivers table, find all the drivers where H3 cell is in this set is available is equal to true and the vehicle type matches, and then we sort it by distance. H3 has one more advantage. It is hierarchical. Resolution 9 for matching at 175 meter granularity, at resolution 7 for search pricing zones at 5-kilometer granularity, at resolution 5 for city level analytics. Same framework, different resolution for different problems. Now, why not keep the spatial index in Redis as a geospatial structure? You might ask this question, right? So Redis GeoAdd and GeoRadius do work, and for moderate scale, this is fine. But at 1.67 million writes per second, Redis geospatial queries under heavy write load become a bottleneck. H3 is a separate service with a purpose-built index that handles this better. Now, here's the summary. Geohash is simple, works with any database, but the edge effects are a problem and not the right choice. For QuadTree, it is adaptive to the density, good for mid-scale problem, hard to distribute, and not the right choice for the Uber scale. Whereas H3, it's a uniform hexagon, hierarchical, and the purpose built for this problem. Uber's production choice is H3. Let's proceed for the further design. Here we are going to discuss about the matching algorithm. Let's trace through the full matching flow. Rider submits a ride request, pickup location, drop-off location, and ride type. The step 1 is ride service calls the pricing service. The pricing service checks the supply-demand ratio for the pickup H3 zone. If the demand exceeds the supply, apply the surge multiplier. Then return the fare estimate, $15 to $20, that is 1.5x the surge. Then step 2 is that the rider confirms. Once the rider confirms, the ride service creates a trip record in PostgreSQL with the matching status. This is the moment that matters for consistency. The trip exists in a database now. Then step 3 is ride service calls for the matching service. The matching service queries the driver spatial index. Then the starting radius is around 3 km and get all available compatible drivers. If no drivers are found at 3 km, then it expands to 5 km. Still none, it will expand to 10 kilometers. And still none after timeout, the trip enters no driver state and notify the rider for retry. When the candidates are found, it gets the latest GPS coordinates from the Redis. It computes the actual ETA, not the straight line distance. It calls the routing service. Then the score of each driver, it gets the ETA with the highest value and the driver rating and the acceptance rate. Now, upon selecting the top candidate, we log them. We update the trip record, driver ID assigned, status transition to driver assigned. This is a PostgreSQL write, and it uses transaction to prevent the double booking. The moment this commits, no other write can claim that driver. After that, we send a push notification to the driver. The new ride request and accept or decline. The driver can either accept this or decline this. Driver has around 15 seconds to respond. Upon accepting, the status moves to driver en route. The rider is notified. Upon decline or timeout, the driver is released and it tries the next candidate. This retry cascade is important. In practice, the first driver accepts most of the time, but you need the fallback. Drivers are busy and have intermittent connectivity or just decline. The system needs to gracefully cascade without a driver waiting for more than 30 seconds total. After this, let's discuss about the real-time location tracking. The location tracking is the highest throughput part of the entire system. 1.67 million GPS updates per second. Let's design it correctly. First, the driver app maintains a persistent WebSocket connection to the location service. Every 3 seconds, the app sends the latitude, longitude, speed, heading, and timestamp. The location service does 4 things with each update. First is write the location to the Redis with key, driver ID, and the value in the JSON format with lat, long, heading, speed, rate, and updated at. Then it sets the TTL of 30 seconds for this. If we do not hear from the driver in next 30 seconds, the key expires. An expired keys mean that the driver is offline and has lost connectivity. The matching service will not dispatch them. Second is update the driver spatial index. Remove the driver from their old H3 cell, add them to the new H3 cell. This happens on every update. Then the third is publish the location event to the Kafka. The topic used is driver location, partitioned by the driver ID. Its consumers are the analytics service, that then demand prediction ML, and then traffic data pipeline. Fourth is, if this driver is currently assigned to a trip, broadcast the location update to the rider. The rider's WebSocket is subscribed to the driver's location. The location service pushes the update directly over the WebSocket. The rider then sees the car moving on the map within 1 second of the actual GPS update. Now, how do you scale the WebSocket connections? One location service cannot hold 50,000 WebSocket connections. Now, at 5 million active drivers plus their riders, you need at least hundreds of servers. We use consistent hashing to route a driver's connection to the specific server. Now, when a rider needs to track a driver, it looks up which server holds a driver's WebSocket and then proxy updates from that server to the rider's server. Now, this is PubSub system pattern over WebSocket. Redis PubSub works for moderate scale. At Uber scale, a dedicated connection gateway service with consistent hashing and internal message passing is the production grade approach. Next, we will discuss about the surge in price. Now, surge pricing is one of the most discussed and the least understood part of the Uber. Let me walk you through it, how it actually works. The fundamental calculation is very simple. Supply divided by demand per geographic location per time window. When demand is low and supply is high, then there is no surge multiplier and it is equal to 1.0. When the demand is high and supply is low, there is a surge. So we increase the multiplier and it can go up to 5.0. But the implementation has many layers. Layer 1 is the defined zone. The city is divided into H3 hexagons at a resolution of 7. Now, each hexagon covers about 5 square kilometers, roughly around our neighborhood. Layer 2 is to calculate the supply per zone. Count all the available drivers in each H3 cell right now. This reads from the driver spatial index, which is updated in real time. Then layer 3 is to calculate demand per zone. Count the ride requests in the last 5 minutes per zone. Then normalize by the historical average for this zone, this time of the day and this time of the week. The raw request count can be noisy and normalized demand is more stable. Then layer 4 is to apply the context signal. Is there a major event nearby, like stadium, concert, or conference? And then what is the weather? Usually rain increases the demand by 20 to 40%. Then what time is it? If it's a rush hour, then a different timeline. These signals come from the ML model trained on historical patterns. Layer 5 will be to compute the surge multiplier. The supply-demand ratio below 0.5 surge, then the multiplier scales from 1.5 to 5.0. If the supply-demand ratio is above 1.0, then there is no surge and the multiplier is 1.0. The exact mapping from ratio to multiplier is tuned to maximize the total rides completed, not just the revenue. Very high surge causes the demand destruction, then the riders give up. This is a bad for drivers and the Uber. The goal is to attract just enough supply to meet the demand. Layer 6 is cache and serve. Now, surge multipliers per zone are pre-computed every 2 minutes. It is stored in Redis. The key is H3 cell ID at a resolution 7 and the value is the multiplier. When a rider requests a fare estimate, the pricing service does a single Redis lookup for the pickup zone. This is some millisecond, no computation at request time. So at a principal engineer level, there can be a question asked that what happens when a surge zone boundary cuts through a city block? Two riders 50 meters apart see different surge multipliers. The answer is smoothen the boundaries. When computing surge for a cell, blend it with the adjacent cells. A weighted average cells where neighboring cells contribute to around 20% to the final multiplier. This prevents jarring cliff effects at the zone boundaries. All right. So now we are going to discuss about the trip state machine. The trip state machine is the source of truth for everything that has happened in a ride. Let me trace the full life cycle. First is requested. The rider submits a ride request. Then we have matching. Fare is confirmed. System is searching for a driver. If the status is no drivers, then no drivers found in the current radius. Retry with the wider radius. If the retry fails with the timeout, we do it cancelled. Then the status is driver assigned. A driver has been selected, waiting for the acceptance. If the driver declines or timeout, back to matching. Try the next candidate. Then we have driver en route. If the driver has accepted, then they are heading to the pickup point. If the rider cancelled, then cancelled. Now, then is arrived. The driver has reached the pickup location. Arrive state triggers notify to the rider, start the arrival timer. If the rider does not show up after the timeout, it is cancelled. The driver is compensated. If it is in progress, the rider has been picked up, the trip is active. GPS tracking is in full effect in that case. Then we have the live ET updates to the rider. If the status is completed, the driver has arrived at the drop-off and then has been marked completed. Upon payment processing, the fare is calculated and payment is charged. Once the status changes to paid, it means the payment is successful. The driver payout is queued and the receipts are sent. Upon the failed payment, the status is set to payment failed and the charge is failed. Then the retry logic kicks in. Every state transition is a PostgreSQL update inside the in progress, and you cannot go from requested directly to the paid. Invalid transitions are rejected at the application layer. Now, why do we need to use the PostgreSQL? It is because the trip state is the one thing that can absolutely must be strongly consistent. Redis would be fast but loses the data on restart. Cassandra is eventually consistent, not safe for the state transition that must not duplicate. Then Postgre with asset transaction is the right choice here. Uber uses MySQL-based systems internally. The same principle. Payment processing is where engineering discipline is the most critical. A bug here means charging a rider twice or paying a driver zero. Both are catastrophic for the trust. The core problem is network failures. You send a charge request to the payment gateway, the network drops and you do not get the response. Did the charge go through? You do not know. If you try blindly, the potential is double charge. If you do not retry, then the potential is missed payment. Then the solution is idempotency keys. Every payment request includes a unique idempotency key, the trip ID. If you send the same trip ID twice, the payment gateway treats it as a same request. In the first call, it charges the card and returns success. If it does the second call again with the same key, it returns the same success response without charging again. The trip ID is the natural idempotency key. The reason being, it is unique per trip and there are no two trips with the same ID. It is generated before the payment attempt and we always know it. So it is stable and do not change across the retries. The payment flow is, this is how the payment flow happens in details. The trip completes, then the fare calculator runs, the base fare plus the distance rate plus the time rate and then multiplied by the surge multiplier. As an example, let's say we have a base of $3 plus 15 kilometers at 1.5 per kilometer, then plus 25 minutes at 0.20 per minute. That totals up to 30.50 and at 1.5x surge, it is $45.75. The payment service calls the payment gateway with idempotency key equal to the trip ID. Non-success, it is recorded in the ledger and calculate the driver payout is calculated by fare minus the platform commission. Typically, it is around 25%. Then it is queued for the payout for driver's weekly settlement. and it sends a receipt to the rider. It notifies the driver about his earning. Then upon failure, we retry with the same idempotency key up to 3 times. If all three fails, then the trip status is made to payment failed. The rider is notified, a debt is recorded. On their next successful payment, the outstanding balance is automatically settled. The rider is never blocked from completing the trip. That last point matters here. The trip completeness, regardless of the payment success. Never block the rider from getting out of the car due to the payment failure. The system handles the payment failures asynchronously. This is a deliberate product decision baked into the system design. Now, let me cover the driver supply prediction. This is a great principal engineer topic. The search system tells driver where the demand is right now. But by the time a driver drives to a search zone, the search may have gone. So the driver supply prediction solve this. Predict where the demand will be in next 15 to 30 minutes and pre-position the drivers over there proactively. The ML model uses this. Historical demand patterns, this zone at this time on this day of week, upcoming events, a hockey game ends in 20 minutes at the stadium, then weather forecast, rain starting in 30 minutes here, then current driver positions and trip completion estimates. When will the driver become available? The current ride completions in progress. It means how many drivers will be free in the next 5 minutes. The output is a heat map of predicted demand per H3 zone for the next 30 minutes. This is surfaced to the driver as the recommendation in the app. It tells head towards a downtown, expected surge starting in 20 minutes. The driver who follow the recommendation gets the first shot at the surge fares. The feedback loop is also important. More drivers pre-position into a predicted surge zone. The supply catches up to demand, surge does not materialize. The ML model learns this dampening effect. Too accurate prediction leads to oversupply and too inaccurate undersupply. So calibrating this loop is an ongoing ML challenge. Now you cannot operate the system without the deep observability. We have multiple observability metrics. One is the location service metrics. In location service, we tell about the WebSocket connection counts. It should be close to active driver count. Then we have the location update throughput. It should be around 1.67 millions per second. Then we have the Redis write latency, P99. If this spikes, the location data goes stale. Then we have the Kafka consumer lag. Another metric is the matching service metrics. We can talk about the time to first match. It will be P50, P95, P99, and the SLO is P95 under 10 seconds. Then the match success rate, then radius expansion rate. After this, we will have the surge pricing metrics. We can talk about the surge multiplier distribution ratio. This is a histogram of current multipliers. Anything above 3x should be watched closely. Then we have the demand to supply ratio per zone, the raw input to the surge model. We should have the payment metrics in which we talk about the payment success rate. It should be above 99%. Then we have the retry per payment attempt. Then we talk about the outstanding debt balance across the users. We talk about the time to driver payout settlement. After that, another metric very important is the trip lifecycle metrics. In that, we talk about average time in matching state. Then we have the driver acceptance rate and the cancellation rate by state. So here we talk about if drivers are declining more than usual, then we need to investigate it. If the rider cancels before the pickup versus after, then it's a very different use cases. So let's bring it all together. So we designed the Uber, a real-time marketplace that connects riders to drivers. The core tension is eventually consistent for the location and strongly consistent for the trip state. Then we discussed about the location pipeline. Around 1.67 million GPS updates per second from 5 million drivers. We talked about the WebSocket connection for low latency bidirectional communication. Then we talked about the Redis for the current location. It is sub-millisecond reads, 30-second TTL. We talked about the Kafka for event streaming to analytics, ML, and traffic. Then we talk about the H3 hexagonal index for the spatial queries. We also talk about the matching algorithm. We talk about how the radius expands from 3 kilometers to 5 kilometers to 10 kilometers. Then we rank the candidates by the road ETA, rating, acceptance rates. And we also talked about the optimistic logging in the Postgres to prevent the double booking. We also talked about the surge pricing solutions. We use H3 resolution for 7 zones across the city. We discussed about the supply-demand ratio per zone, then the updates every 2 minutes. We pre-computed and cached in Redis the sub-millisecond lookup at the request time. Then the boundary smoothing prevents cliff effects at the zone edges. We also talk about the trip state machine. 8 states from requested to paid. Every transition is a PostgreSQL transaction. The idempotency keys prevent the duplicate payment charges. Temporal or a similar workflow engine handles retry and the compensation logic. We also discuss some of the principal engineer concerns. We discuss about the double booking, then the mid-match crashes, then GPS spoofing, and peak event loading. The key insight about Uber's architecture is that the system is partitioned by city. Each city is almost independent. That isolation reduces the blast radius enormously. A bug in Sao Paulo matching service does not affect the London. We design a city level isolation, then add cross city infrastructure where needed. If you're preparing for the system design interview, this video plus the Google Maps video cover the core geospatial and geo distribution real-time systems. Now subscribe to Yoda Monk for more and see you in the next one.